Well, as you see from the numbers in the way, not my original. We're talking, I don't know whether you like it or not. I think, I didn't know what to expect. I was sort of preparing for like a long discussion. Let's say, being afraid that people like sitting there without any reaction. I think it's much better if we actually talk and discuss and we meet stuff. So, as you see, I moved on and I moved back later. I think it will be much more productive. I mean, if you want, I can go back to my schedule. I think it's boring. So, let me get to this new one, because this is a very nice idea that it's taking, well, I would say it's oversold right now, so it's overemphasized, but I think it's very nice in many, it has several very nice ideas that actually can give you some good background also for new research or new things that you can see, new ideas that you can see. It's called extracting knowledge from execution. The famous name, or quote-unquote famous name, is DICOT, because the tool that, the methodology that was first introduced in DICOT, and is still the major one, but there are several others that are actually coming out. So far we've looked at a couple of analysis techniques, which are simple checks, which you can do at runtime efficiently and can give you good feedback and good information. Now we go to different kind of things, and that's a point. We can get, let's say, when you execute a program, you get a lot of information. Okay? Most of which is lost. If I ask you, for example, have you ever tried to use PowerPoint with a given specific feature? Do you know that? Anyone? Probably you can't answer to the question, because the question is, you may or may not. Unless, well, of course, if I ask, have you ever pressed that button, you may remember. But if I ask, did you ever had the chance to exercise, for example, let's say, the part of PowerPoint that changes the background? And you might say yes, you might say no, you might say no, and that means yes, you might say yes, and it's not completely, because the question is, you may have done it implicitly by using another features, for example, by selecting the slide style, or you may have not done in the way they're actually supposed to do even if you selected the background. So basically, when you run the program, you get a lot of information that you forget. And so it's a very easy thing, which is, well, why don't we trace program executions? And people do trace program execution. So you trace the program execution, and you look at the program and the trace and say, yeah, it was bad or good. The tracing program executions gives you, it's done, for example, in debugging, we do that. Okay, it's done in many specific environments. It's usually not done at runtime because of the overhead. Or partially done. And in general, the big problem is that how many of you are willing, how much memory you want to dedicate to the tracing?
What?
10% of your memory? 100%? 200%? Software traces are huge. So the problem is, if you start tracing the program and you get to this tracing, to this huge trace, after a very little while, you don't have enough memory for it. So this is a very nice idea, which is, can we, instead of save the whole trace, extract part of it? Okay, and I'll show you how we can do that. Okay, for example, that's a very simple example. This is a piece of code taken from a basic program book. I think it's, I forgot the name, but it's one of the books that's sold in, I think it's White, this guy from the US who wrote this book. It's a very popular book, actually, on algorithms. And that is this very simple ABI node insert. Now, I'm sure that most of you would actually understand what the code is by reading the ABI node insert. Okay? Because I'm sure you all know what an ABI tree is, and insert means basically that the difference between father and the right and the left children in the tree is less than 1. Okay? So that's the kind of information that you like to actually know that it's true on your code. Okay? So this is a specific specification says A, B, and tree where the difference in depth of the different children is at most 1, plus or minus, right? Does this actually satisfy this problem? And we can actually look at that and see if that's actually a simple problem. So let's get to 2 different scenarios. One is the code is a bit more complicated than that. Okay, or we call it the property is more complicated than that. Or you have the code and you don't have the specification. You want to know what are the exact properties of the code. Okay, now, again, I tell you how can I do that. I can actually run the code, keep the trace, run the code, keep the trace, run the code, keep the trace, and then go through the trace and see yes, it's satisfied. No. Okay, the thing that I can do is actually this one. I start with a set of predicates. And I tell you what the ideal situation is. This is all the possible predicates in the world. So I say, let's say everything which can be true in this program. And then I execute the program and I delete the violated predicates. Okay? That's almost a little bit more. Now, how do I start and how do I work? Okay, I start with this set of predicates. Now, the idea is they have templates. So, for example, every time you have a variable, you can actually instantiate the predicate that x is equal to a constant value. Anytime you have a variable, if you say x is not initialized, or x belongs to a small set of values, or x is greater than a given value, or less than a given number, or it's included in 2 values, or it's not 0, or it is 0, or it is equal to given value modulo b, or it's not equal to a modulo b, or if you have 2 numeric variables, they actually are linearly dependent, or they have similar relations. Now, of course, I can get through huge number of invariants, right? And infinite numbers, because x equal a may have infinite different possibilities. But you can start with this sort of, let me call it implicit way of having variables. So it's not really true, but I can say, okay, I know what is the set of possible assertions or invariants on a single variable. Let's focus on one single variable for the moment. Okay? Now, I don't want to really list all the possible invariants right now. Okay? But let's assume that I start executing the program, and for example, my father, there should be father somewhere here, my right gets value 5, okay, or gets, whatever, So, after one single execution, I can already get a very small set of predicates, So, let's say if I run the program and I have, for example, a variable, I can say, x can be equal to every possible value, but if the first time I run it, it's equal to 5, that's the only value can be possible. So, the only variant is x equals 5. Okay, 5 is a fake number, of course, Then, or if through that run is not initialized, it may be constantly, always not initialized. Okay, of course it may also belong to a small set of values, so it's also greater than 0, so I can, after one run, I can actually set up my final set of possible invariants, equal to a constant, in a set, not initialized, not 0, greater than 0, less than 0, and greater than another one. And so I get a reasonable finite set of variables. Next, second execution. It is 7. So if it's value 7, then it's not constant, obviously. It's either 5 or 7. And it's not initialized. And it's positive, it's not 0. And it's greater than y, which is always 5. And it's less than z, which is always 10. Okay, so I get, and the idea is, while I execute the program, instead of keeping the whole possible traces, what I do is I actually delete, step by step, the specific kinds of, the specific kind of invariants that are violated. Okay, and it's not really a deletion in this way, so I start and say, it's 5 this time, and then it's 5 or 7, and it's 5 or 7 or 8, And eventually I get to a point, let's say, so for example, I start with this one. This one says I create an ADL tree, okay, then I insert 5, then I insert 2, then I insert 7, right? That's the second test case that I see you. That's the second test. So I run it for this simple test case. I create one in one tree. Then I run to the second one, which starts with a random number of test cases and generates inserts 100 or several possible values. Okay, 2 different test cases. Now, let me start and look. Okay, let me hide this part. Okay, yes, that works well. Okay, first test case. Okay, first test case is this one. Okay, I get this information. Father is 2 or 5 or 7. If you know how an ADL tree insertion may work, you can guess that if my only test case says insert 2 and then insert 5 and then insert 7, okay, the value of father through all the possible executions so far is either 5 or 2 or 7. Then the left is constantly 2 because basically what I do, I generate a tree which is basically 5 to 7, alright? So, by the way I generate, I actually create a new node and then insert it. So the value of father becomes 2, 5, and 7. Okay, in different. The value of left is only 2. The value of right is only 7. Left height, which is the depth of the left tree, is equal to right height. Okay, right height is equal to diff height. Okay, so I have 3 variables: diff height, left height, right height. Left height is actually the depth left-hand side, right height is depth right-hand side, and diff is actually the difference. Okay, the main difference. Left height is 0 because it's actually a complete tree. Right height is 0, and father height is either moved from 0 to 1. Okay? Now, you see, I have some information which is not just related to the specific execution of this mode general, and the information says basically, yes, some information is useful, some other is useless. And some information tells me that the program is correct. Some other information tells me that the program has not been tested enough. Which is probably the case, since I actually have only three nodes. Okay, one information is left is equal to 2. Come on, it's not possible. So this is correct, but it says the test has not been executed enough, because it says you only have one left child in this case. This is also correct, but says, the test case is not enough. Some other, like this one, is basically, the tree is perfectly balanced and so what. I mean, this is a special case. So again, it's what I say here in one single word is limited validity. So the technique is fairly simple. I execute the test case. First, I identify. Well, that's the thing. I execute the test case, I monitor each possible execution, I look at the value of all the variables, and I actually mark my sets, and I say, okay, at the end of the execution, this is what was true during the execution. Okay? And I get some information. Now, let's see what I get in the second case, and then let's try to understand how it works. Same program, same technology, different test cases. Now I run with more test cases, and you say I get father is greater than 0. Left is greater than 0. Father is greater than left. Father is less than right. Left is less than right. Father height is greater or equal to 0. Left height is greater or equal to 0. Right height is greater or equal to 0. Father height, blah, blah, blah. Diff height is either -1 or 0 or 1. Okay? And the difference between left height and right height plus the diff height is 0. And this actually tells you that that's exactly the insertion in an ADL tree. It's balanced, it's left, it's sorted, and all the properties are good. Okay. Now, let's understand. Okay, I have some information which is useless, further greater than 0. It happens to be because my test case is always greater than 0, doesn't tell you much. I get some information that is important, which is all the elements are non-negative, some information that says the argument works correctly, and the tree is balanced. Okay? So, and this is not something that I get a specification, it is something that I get out of the code. Now, I hope you can already appreciate the difference between getting 1 million traces and getting this set of environments. Okay. Now, let's get a couple of more information, which is how the system really works and how. Let's see if I get. How do I actually get this information? So the system really works by marking the point of the program where I want to monitor the program variables. In principle, I can monitor everywhere. In practice, it doesn't make sense to look at the variables everywhere. So I say, okay, after the insertion, this must be always true. Okay, so I may say, okay, during the insertion, I don't really care, but after it must be true. Okay, so I may decide to monitor variables only at the beginning of the function, at the end of the function, at the end of the loop, and that's of course something that is easy to guess. For example, I can actually, say, I want to monitor the program at any time I would actually put some assertion. I may also select a subset of variables. Of course, depending on the variables, it may be easier or more difficult to find the element. And now I may actually, and that's actually simple to understand. The second thing is, why the hell this I have father 1 of 257 and this is the father greater than 0? Isn't this greater than 0? Can you guess why the tool is fully automatically generate this one in one case and that one in another case?
Probably the set is too big.
Yeah. So it's not the set is too big, the probability of being true is high. So it's a bit more oh no, it's not. I thought it was here, but that's a different slide. Okay, so let me tell you this. Okay, I run one execution and I get 5. What is the probability that is actually that it is actually by chance greater than 0, and what is the probability that it is actually greater than 0? So one value does not tell me anything. And I'm sure you get also some good probability courses to understand how to compute probability. Okay, I'm sure you can do better than me in saying something like, what is the probability that an assertion is by chance correct, or what is the probability that is actually correct? And it's not a matter of computing the probability of that assertion to be true out of all possible cases. Okay, so if I run, let's say. 100 executions and all are greater than 0, then it's actually probably true. If I run 1 and it's 5, I don't only have that much. If I run 10 cases and I always get 5, it's highly probable that it's going to be 5. So basically, I don't want to go to the detail because it's actually 5 to end of the course. So I don't want to really get into the details, but you can see, and it's easy to check on the books, it can see that you can actually go through, you can compute the probability of each assertion to be true incrementally, and decide that at some point you can move from that assertion to this one, not only because the set is too big, because if you always have like even a reasonably small set would actually be likely to be true that it's always possible. And so you get a filter that says, oh, this is by chance that happens, and this is actually not by chance, that is really highly probable that it's actually a true problem. Okay, couple of more observations. So far, program, monitor the executions, invariance on the program. Right? Now next, what do I get? I don't get a specification. That's not a specification. It's not even a complete description of the program behavior. It is a description of the program behavior experienced so far. Okay? So, what I get is something which is true, maybe true only on the portion of the space that I explored so far. But of course, I do have, I can estimate the probability that it's actually true by chance. Okay, so this tells you not that the program specification are blah, blah, blah. It doesn't tell you even not that all the possible executions are like that. It tells you that so far I explored that space. So how do I make, what use can I make of that? Oh, by the way, for example, okay, that's what the slide I was looking for before. Further positive, one execution, 50% of probability. Further positive, n executions, 0.5 to the n% of probability. Okay, so I put a threshold and say, okay, I need at least a given number of executions, all positive, to be able to say that it is positive. So I can actually reduce the possibility of being actually coincidentally true. Okay, but which is what. Let me actually see what I actually want to do with it. I can do testing. I can use it in testing. I have a specification. I derive my test cases, and I know what the space of the execution should be. I get my invariants, and they tell me what the space of the execution I really explored. So I can actually compare the explored part of the space with the whole space. And I can get information about, oh yes, there is a complete space of the execution which has not been explored yet. Okay? I can use an analysis. I have a program, I don't know what it does. So if I give you, if I give you the ADL tree, I hope you actually understand it from the code. But if I give you a black box program, let's say, I give you this program in Bliss. Do you know Bliss? Okay, great. So I give you this program in Bliss, and I ask you, what the hell does it do? But I give you, I say, oh, by the way, and if you execute it with 100 random values, you get this behavioral model. Can you tell me what it does? More likely. So, it's a set of additional information that helps you understanding what the program does exactly, okay? You can use this in regression testing. In fact, this is something that we did actually, which is we executed the program with a different kind of model. So this is actually a model based on logic. So you get logical assertions on the program. We did actually a different one which extracts final state machines that represent the actual behavior of the program, and we use that for regression testing because it tells you what are, basically it tells you whether the new version executed with the test cases maps on the same space or not. So it tells you something about what has changed in the new version. And we use that also for getting information about compatibility in different versions. So one thing which is actually important is the new version compatible with the old one or not? But with the same test cases, you produce the same invariants, it's more likely to be compatible than if you don't. You can use it for component-based testing software, and that's another thing that we did, which is you actually have a huge system, and at some point you want to exchange a computer per component with another one. Are they compatible? Run the same test cases, build the model of the behavior, compare the models, and you get an answer. And you can get result dynamic, for example, because you get out of all the test cases, which one are actually out of the scope of life. Okay, it's almost lunchtime, I guess. Now I'm correct, and I'm finished. I finished that part. I have alloy and relational algebra. Since a subset of you already know alloy, I don't want to go through that. Okay, let me just tell you one little thing, which is, as I mentioned, you may not see it very well because the resolution is bad, but this is the cover of the book that I just wrote. It was published last year by John Wiley. And what I did was, I cannot give you the full book in PDF because my editor would be crazy, but I extracted a few chapters and I sent them to Sasha, who will send them to you, so please don't distribute them. If you want to sort of, let's say, what I did today was basically half of the time just walking through the general problems, and half of the time concentrating on some simple analysis techniques, just to give you a flavor. Tomorrow we'll actually have half of the time, which is not enough, but We'll work on either data flow testing or functional testing. We'll decide tomorrow morning and we'll think about that. Let's say, out of what I send you, if you get chapter 9 program analysis, it summarizes the pattern analysis, right? So if you want to know a bit more about how to compute the probability of a icon, how to get the model for loss of analysis, how dynamic analysis works, you get a bit more than just a quick introduction in the class through this chapter, right? The other thing is, if you type my name or my co-author's name, Michael Young or both of them, you quickly go to, or you can type like Mauro Pezz testing or analysis, you quickly go to the website of the book, which is something in Oregon. So it's www.csu.oregon, blah, blah, blah. That's what you get. Or you get to my website, there is a pointer there, and there are some sample chapters available. So you get chapter 1 and 2. And chapter 1 and 2 has most of the discussion about the 5 major questions, the properties, the trade-offs, the parameters. So you want to know more about this, you read something more. It's not a lot. I mean, each chapter is about 10-15 pages, and you get like couple of pages explaining better this non-orthogonal dimensions if you want to get information. Of course, I can also give you the slides, but honestly, I think slides are very bad as learning material because you can at most walk through and say, I remember that time you actually walked in that part, you said something, and you got confused. Slides are not useful to remember what I said and not to learn a bit more. So I send after lunch, I'll go to the hotel and send it to you and then you send it to them. The only recommendation is trash it, don't read it, don't distribute it. Okay, I'll let you go for lunch and you'll see Natasha at what time?
Just in 1 hour.
Oh, in 1 hour. And then we'll meet again tomorrow morning. Okay?